Good day, everyone, and welcome back to the LRC. This is the fourth and last episode that we are going to be doing for Combinatorics, so congratulations for making it this far. And today we are going to be talking about combinations. So let's get right into it, shall we? What is the definition of a combination? While this math term sounds very similar to permutations, the definition of a combination is a grouping of terms or objects or items, but the order doesn't matter. This means, as you can see over here, AB does equal to BA, and something like 1, 2, 3, 4 is equal to 4, 3, 2, 1. They are all the exact same. Now, the formula for combinations is pretty simple. It is just n factorial over n minus r factorial times r factorial. And this is basically the same as the permutations, except there is this little addition of an r factorial over here. Now, just to illustrate what that would look like if you were to put that with some real numbers, we have an example over here. Instead of just having 7 factorial over 7 minus 2 factorial, which would be 5 factorial, you would have 7 factorial over 5 factorial times 2 factorial, which leads to this bigger number, and it leads to the number that you eventually get for the combinations being a lot smaller. Now, this may be a pretty simple addition, but if you don't understand the context behind it, it can make combinations feel a lot really complicated and really hard to understand. And that's what we're here today to talk about. We in the LRC pride ourselves in explaining the meanings behind formulas. So today we're going to not only talk about the combination formula, but also how to understand and comprehend why we have this extra r factorial over here. Okay, that's enough yapping from me. Let's move on to what you came to this video for. Why does n factorial over n minus r factorial times r factorial work? The first thing we're gonna have to tackle here is the fundamental difference between combinations and permutations. We already know that for permutations, order matters, and for combinations, order doesn't. But what that looks like in real life is if we were to just use the permutation formula to count combinations, we would be doing something known as double counting. You see, since order matters for permutations, let's say we're taking three objects, right? We're supposed to order three objects. We would have different ways of ordering it. You could have 1, 2, 3, 3, 2, 1, 2, 3, 1, and all of these things would be counted as a separate thing, right? So these would be three total permutations. However, since order doesn't matter for combinations, all of these examples would simply be considered one combination. So how do we get rid of the double counting? We can actually see it already in this expression. We get rid of the double counting by using r factorial. Now, why does that work? The reason this works is because of one of the main principles of factorials. If you have a factorial, we always know that the factorial shows you how many different ways you can order that number of objects. So 5 factorial will always show you how many different ways you can order 5 objects around. If you don't really know the reason why, you can go back to our FCP video, you can go back to our permutations video. But just to give you a brief summary why, it has something to do with fundamental counting principle. You see, you can choose to have 5 options for slot 1. You have 5 different options to put in slot 1, 4 different options to put in slot 2, so on and so forth. And those happen to be the exact same numbers in 5 factorial. So 5 factorial shows you how many different ways you can order and rearrange 5 different objects. And what we want to add to this equation is a way to divide all of is a way to get rid of all of the ways you can rearrange the set of objects that we're considering, r factorial. So all we really have to add to this expression is r factorial and divide that by the number we end up getting from here so that we can get rid of all of the cases of rearranged objects. That all sounds a bit abstract, I'm sure. So let me try and showcase this with like a 7 choose 5, right? 7 choose 5. Um, in this situation, 7 factorial would be up top here, and then this would be 7 minus 5 factorial times 5 factorial. Now, this 5 factorial shows us how many different ways we can rearrange all of the objects, right? But since we don't want to consider that, since no matter how many ways you rearrange the objects, it's all just going to be one combination. Dividing this 5 factorial from the 7 factorial we end up getting will take out all of those chances of double counting and will make it so that we find the actual combinations, not just more permutations. Um, yeah, that's it. Okay, now that we're done explaining how the formula works, it's time to get into the hard part of this lesson, application. Math teachers, especially at higher levels, love trying to stretch the lesson into problems that challenge your logic. So we're going to be tackling a significantly higher level problem here with what we've learned and showing the logic behind it. Now, for combination problems, the things that are usually done to make it harder is the addition of multiple conditions. Something especially evident in the problem I chose to solve for you today, this one. A team of 4 has to be selected from 6 boys and 4 girls. How many different ways can the team be selected if there must be at least one boy and girl in the team? Now, the first thing you always have to ask for hard problems, as I said in the permutations video, is why can't you just use the formula here? You could just theoretically use 10 choose 4 and then just plug in the numbers. You get 10 factorial over 10 minus 4 factorial, blah, 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 whatever. The reason you can't do that is, unfortunately, you have multiple different ways you can draft a team. As you see here, you can have 3 girls and 1 boy. You can have 2 girls and 2 boys. And you can have 1 girl and 3 boys. Because as long as it is 1 boy and 1 girl in the team, it is a valid team. So you have to calculate and you have to consider the multiple different team structures that could arise from that condition. Now, after you figure out the small little trick that the small little trick the math teachers would have for you there, it's actually pretty easy to solve this problem. You just kind of have to break it down into multiple parts. Now, to solve this problem, all you really have to do is just multiply the different options by each other. So if you want to choose 1 boy from a group of 6, you do it 6 choose 1. And then if you want to choose 3 girls from a group of 4, you do a 4 choose 3. Multiply those together, you get your answer, and same goes for the rest of these. Now you may be wondering why you are adding over here rather than multiplying like over here. And the reason that happens is because fundamental counting principle only works if you're trying to calculate for possibilities. Okay? Uh, and this is going to get a bit complicated, so stay with me here. All of these things are options that lead to different possibilities. They're like things you can mix and match. Whereas the answers that they give aren't options. You don't have 24 different team options that you can mix and match with the other 90 different team options. You have the already existing teams. If I were to compare this with something, right? Let's say you have like you're wearing like pants, a shirt, and shoes. You have, let's say, 7 pants, 3 shoes, and 1 shirt. If you multiply all those together, you get 21 different outfits. But if, let's say, your friend, right, wants to make a wants to do that also, he also has 7 pairs of pants, 3 pairs of shoes, and 1 shirt, and he can make 21 different outfits. If you try and calculate how many outfits you have together, you don't multiply 21 by 21 because the outfits are already formed. You can't just merge them together or make something new with them. Since the outfits already exist, you have to add them together because you can't mix and match the already existing outfits. In the same way, because these are already teams and not options for teams, they're not people you can mix and match to make a team. All you can really do with them is add them. I hope that makes sense. If it doesn't, then feel free to comment and I'll try to like explain it a bit more in the comment, or feel free to do your own research. But yeah, that's basically why you can't just multiply the numbers by each other. And yeah, that's it for combinations, and that's it for the rest of combinatorics. I hope you guys enjoyed this video as much as I enjoyed making it. I hope you guys learned a bit more. I hope you guys rewatch it if you're really unsure about what I said. And I hope you guys ace all of your math tests and do really well in life with what we've taught you in LRC. Thank you very much for always watching, and we'll see you guys in the next playlists that we make. Bye bye.